We should start the final session, basically run by Bobby. So he will give a talk first. Bobby, please go ahead.
Thanks, Miriam. Thanks to Jason as well for helping to co-organize this meeting, and to everyone else that's contributed. So yeah, I had a sort of general title, which was New G2 Manifolds and Their Physical Interpretation. But I guess really what I'm talking about, what I've decided to talk about in the end, is the physics of codimension 6 singularities inside G2 holonomy spaces. So there's a strong connection between Calabi-Yau threefolds with certain kinds of codimension 6 singularities, like, for example, conical singularities, and 5-dimensional superconformal field theories. The existence of such theories, so these are quantum field theories in Minkowski spacetime of 5 dimensions, and they originally go back to the work of Seiberg, who proved that they exist. It's rather surprising to find non-trivial interacting field theories with conformal invariance above 4 space-time dimensions. Now, Dave and Nati wrote some papers which showed that these naturally arise by considering M theory on a Calabi-Yau threefold with a codimension 6 singularity. And so essentially there's a correspondence between certain singular Calabi-Yau threefolds and 5-dimensional superconformal field theories. These theories are rather mysterious. We don't really understand too much about them, apart from things like we understand their symmetry groups, or symmetry properties, a few other, some of their sort of topological properties. They contain exotic forms of matter, and so these interacting field theories, the matter is not described by any approximation in which you can just use fields like we do in, say, the standard model of particle physics. So it's really important to try and understand what these things are, and even to try and classify them in some way. And there is work in our collaboration, especially due to Sakura and collaborators over the years, and several other groups as well, and people. Probably this is a rather incomplete list of names, so I apologize for that. Now, the question that I want to ask, which probably will take several years to understand properly, but it'd be good to embark on this question now, I think, is what is the physics of a codimension 6 singularity inside a G2 holonomy space? So locally, such a singularity will be, the topology of such a singularity will be the same as that of a Calabi-Yau example, just because of the way the holonomy, near the singularity, the G2 holonomy will, G2 holonomy group will break to locally SU3 times the trivial holonomy group. So that already shows you that such a singularity is one that arises in a Calabi-Yau threefold in general. So what I'm going to do in this talk is make some very general remarks about such theories. Then I'm going to introduce a rather large class of examples, and then I'm going to study one particular case. So part of this, in particular, the example that we'll study is some work in progress with JSON. There's some related work that I'm doing with Jonathan Heckman and Michele Del Zotto, but I'm not going to speak about that in much detail. That work, we'll leave that for one of the future meetings, I think. Okay, so the general picture in 5 dimensions is like this. You have a Calabi-Yau threefold Z with an isolated codimension 6 singularity, and living at that singularity is one of these exotic superconformal field theories that arises in the case of, if you consider this as a background for M theory. The symmetries of such a, let's talk about the symmetries of such a system. Well, it has the 5-dimensional Lorentz symmetry, or its spin cover, since the theory has fermions and supersymmetry. There could be some global symmetry group G. And in addition to that, you have, the Poincaré group gets extended to the superconformal Poincaré group. So if you like, the Lie algebra of the Lie algebra of that group is a bi-graded super algebra. Now, the symmetry group G has a natural geometric interpretation. This global symmetry group G comes from codimension 4 singularities of Z of the orbifold type, and in particular, since Z in general is we can take it to be non-compact since we're not considering gravity here. We're talking about codimension 4 orbifold singularities supported on non-compact curves. If the curves were compact, then you would actually get gauge symmetries in addition to the global symmetry. And the question we want to ask is what happens if this type of singularity occurs inside a G2 holonomy space X? Well, if that occurs, let's consider it from the point of view of the 5D effective theory, without worrying about the details of Z and X for the moment. Well, then we know that the system that we started off with that has 5-dimensional supersymmetry, that then has to get broken to 4-dimensional supersymmetry. And the 5D Lorentz symmetry gets broken to 4D Lorentz symmetry. And G itself could break to G, could remain intact, or it could break to a subgroup in general. But this actually turns out to depend on details. So from a field theory point of view, we can just make some very general analysis. So we want to consider a 5-dimensional theory, but on a space-time that has only 4-dimensional Lorentz invariants. Well, that then essentially restricts us to consider 4 cases, which I'm calling 0, 1, 2, and 3. So we'll take the metric, we'll take the manifold to actually split off. In order to have 4-dimensional Lorentz invariants, one direction has to split off, but we need to keep Minkowski spacetime intact. And you could consider metrics preserving different amounts of different kinds of metrics on this space. What we're going to consider here are cases 1 and 3. So case 0, if we assume for simplicity that the 5-dimensional metric is flat, then case 0 is just has the full symmetry as the original theory, and case 2 is just the compactification of the original theory down to 4 dimensions on a circle. So the more interesting cases are the cases with boundaries, which is case 1 and 3. So in case 3, I here means a line segment. So here I'm going to essentially stick to the case where we've got a flat space-time metric. And in the other paper that I mentioned, there we're actually considering essentially warped products. So in the flat case, then case 1, the semi-infinite line is then actually naturally thought of as an orbifold. So R mod Z2, where the Z2 takes the coordinate Y in the 5th dimension and sends it to minus itself. Similarly, case 3, the line segment, we take the coordinate Y and send it to minus itself, and then view the line segment as S1 mod this orientation reversing symmetry. And those are the cases that we will think about. So then we should ask, how does the Z2 act on states in the theory? Where by assumption, we want to preserve 4-dimensional n equals 1 supersymmetry, which is the condition that arises from the fact that we're imagining this system to arise in a G2 holonomy manifold. And the answer to that question is that actually this Z2 as a physical symmetry is what's called the CP, a CP symmetry, where P stands for parity. So here we're considering a sort of generalized parity symmetry in which only one coordinate is being reflected, and C is what's called the charge conjugation symmetry, which sometimes one views that as symmetry which takes particles to antiparticles, if one wants to use the language of particles and antiparticles. Just a side remark, CP is subtly violated in the real world, and this leads to subtle differences between particles and antiparticles. This has to be true anyway, because since the universe contains much more matter than it does antimatter. And the geometric interpretation of both of these cases is given here. So in case 1, we consider a G2 manifold, which starts with our original Calabi-Yau manifold that was given us a 5-dimensional theory, which we're calling Z. We take the flat product with a real line, and then the Z2, then we have a quotient by Z2, which is acting on the 7 manifold in some way that is described below. And in the case of case 3, the action is essentially the same, just that instead of having a copy of R, we've now got a copy of S1. So if Z, small omega and big omega is a Calabi-Yau structure on Z, then X can be endowed with a G2 structure phi, which is written down there. And the Z2 acts in the following way. It reflects it's a parity transformation in the Y direction, and it acts on Z essentially as complex conjugation. So in other words, sigma is a real structure on Z, which acts on the Calabi-Yau structure as described at the bottom. So it reverses the sign of the Kähler form and complex conjugates the holomorphic form. And you see the fact that sigma acts as complex conjugation naturally identifies it as a charge conjugation operator, because it will take representations to their complex conjugates, for example. So obviously, in everything that I'm talking about, one is requiring that, one assumes that one has a Calabi-Yau structure that admits an appropriate anti-holomorphic involution sigma. So these sorts of G2 orbifolds have been considered for quite some time in the literature, in particular by Dominic and Spiro more recently, mostly in a compact setting. Here, since our Calabi-Yau that provides us with the background for this 5-dimensional superconformal field theory is non-compact, we're interested in the non-compact setting, but I'll say a few words about the compact setting at the end, towards the end. So using this sort of geometric embedding, one can make some rather general remarks. So in the 5-dimensional theories that arise from M-theory on Z, a key role is played by compact holomorphic divisors in Z. In particular, the holomorphic divisors which essentially collapse to a point at the singularity, at the codimension 6 singularity. These are very important because M-theory contains M5 branes, which are these 5 + 1 dimensional objects, so 5 spatial dimensions. And since the divisor is holomorphic, it's calibrated, and that means that M5 branes wrapped around such a divisor. If you imagine a configuration in which 4 of the spatial directions of the 5 brane are wrapping this divisor. So if we assume that this divisor is a smooth submanifold, for example, it would actually be a 4-manifold, and the fact that D is compact means that in the effective theory, you have an additional dimension left over, and so these objects look like strings in 5 dimensions. And since the divisor collapses at the singularity, it means that the mass per unit length of these strings is going to 0. And this is a sort of formula that we can trust because these objects are supersymmetric, or in this case, holomorphic. Now, there's an analogous statement one can make for the G2 case. So now we're modding out by this anti-holomorphic involution. Well, typically, though probably not generally, typically sigma will act as a real structure on these divisors. And now the complex conjugation of the divisor, given its dimension, says that the orientation is actually preserved. So the actual homology class of D will typically be preserved in the quotient. So that actually means that in the G2 orbifold, such Ds will be co-associative or supersymmetric cycles in this G2 orbifold X. And that then means that the 5 branes which wrap such Ds are also supersymmetric or BPS strings whose tensions or equivalently mass per unit lengths go to 0 at the singularity. And what this means, these sorts of systems in various contexts, in various dimensions, tend to produce interesting 4-dimensional, interesting physics in this sort of limit. So this is sort of general expectation about these sorts of systems that we expect an interesting 4-dimensional theory to emerge from these setups. Now, if the involution has fixed points, then X actually has a codimension for A1 singularity. And that tells us then on general grounds that these systems have an SU2 global symmetry in general, which is located at the origin in the R direction, or in the case of when we're considering S1 instead of R, at the two fixed points of at the two ends of the line segment, if you like. So in that case, you would have two SU2 symmetries. Now, that SU2 symmetry is localized along a special Lagrangian submanifold L in Z, which is the fixed point set of sigma in Z. And so if the intersection between L and this divisor is non-empty, then we might also expect something interesting to happen there in general. So now I'm going to introduce a large class of examples. So in these examples, we're actually going to consider a flat G2 structure. So this sort of goes back to the kinds of things that Dominic was considering in the 90s. So we want to start with a situation in which the codimension 6 singularity is an orbifold singularity. And one can, so for such singularities, the space is modeled on, the Calabi-Yau space is modeled on C3 mod gamma, where gamma is any finite subgroup of SU3. So, and in this case, we can be very explicit about our Z2 action. It's just complex conjugation on C3, and y goes to minus y as usual. And the group that's generated by this is obviously a finite subgroup of G2 for all gamma. But these haven't really been systematically, these groups haven't really been systematically studied in the physics literature, as far as I know. Now, let's talk about the 5-dimensional theory a bit. So C3 mod gamma, so we know from work of Rowan, Ito, Reed, many others, that for all gamma, so there is a classification of finite subgroups of SU3 and G2 as well. It's known by this series of works that culminated in Rowan's paper that such orbifolds admit at least one Crepant resolution. And so that's our candidate for the 6, for the Calabi-Yau manifold, although in general, I guess not so much is known about the Calabi-Yau metrics for general gamma, what sort of Calabi-Yau metrics that we have. But anyway, it's expected that if you collapse the if you collapse the exceptional divisors of this resolution to the orbifold point, that is in that limit one obtains a 5-dimensional superconformal field theory. Now, as far as I know, these are only well studied for abelian, for when gamma is abelian, because then you have a toric. You can understand the Calabi-Yau manifolds and aspects of the metric using the fact that it's a toric singularity. But for general gamma, it's not really, hasn't been studied in much detail as far as I know. I want to mention, actually, as part of this collaboration, we are studying some non-abelian cases with Neil Lambert, Marwan Najjar, and Eric Svanes, but I'm not going to talk about that here. Just a word about what resolving means. So physically, this means that we go into what's called the Coulomb branch, and since the Calabi-Yau is now smooth, one has a low energy description in terms of a weakly coupled gauge theory. So there are various questions one can ask, like what is the physics of M theory on R7 mod G prime, where G prime is any finite subgroup of G2? For the class of examples that I'm considering here, one can ask things like, when can we actually desingularize this space, producing a 7-manifold of G2 holonomy? And I'll finish by describing one example that Jason and I have been studying. So this is the case where gamma, the finite subgroup of SU3 gamma, is actually the center of SU3. So it's a rather special example. And in that case, there's a unique Crepant resolution, and the total space of which is O of -3 over CP2. And it's known, that this manifold admits a very symmetric, complete metric of SU3 holonomy that was originally written down by Calabi. And this metric is asymptotically conical, in fact, asymptotically locally Euclidean. So it's a cone over S5 mod Z3. Now, the complex conjugation in this space just fixes you to the real points. So since the total space is O of -3 of CP2, the fixed point set L of the involution is O of -3 of RP2. So it's a sort of real line bundle over RP2, which topologically you can think of as R times S2 modulo a Z2, which reverses the orientation of both factors. And physically, we have an A1 singularity along this 3-manifold. Now, if we consider the work of Dominic and Spiro, what they showed in the compact case is that if the fixed point set has a nowhere zero harmonic 1 form, or a Z2 twisted harmonic 1 form, then one can resolve the singularities along the fixed point set, along L in this case, by gluing in a copy of the Iguchi-Hansen 4-manifold times L, or in the Z2 twisted case, there's an overall quotient by an involution. And I remind you that the Iguchi-Hansen space as a manifold is the cotangent bundle of S2. Now that's in the compact case. Now we're in a non-compact case, but so what can one say? Well, if the 1 form, let's call it alpha, is L2 normalizable and decays sufficiently fast, one expects some of their results ought to go through. But now we also have to think about the metric at infinity. Essentially, in order to apply their results, one needs that the induced metric on the 3-manifold becomes locally flat at infinity, because that's the sort of model that they're starting with in their construction. And somewhat remarkably, probably, this turns out to be, all of these things turn out to be true for the example that we are studying. So I'm not going to give any details here, but this space admits a nowhere zero Z2 twisted harmonic 1 form with very fast decay at infinity, and the induced metric is flat at infinity. So this then will likely give rise to 2 new G2 holonomy manifolds, 2 cases, because we can either do it with R or S1 with Betti numbers that I've written down here. But in general, one wants to consider this problem for general finite subgroups of SU3. Miriam, if I have 1 minute, I just wanted to make a couple of comments about the compact case, and then I'll stop. It won't take very long. So actually, one can think about this example in a compact setting. So we were starting with C3 mod Z3, but actually one could start with T6 mod Z3 instead, where I'm thinking of T6 as a product of 3 elliptic curves whose lattices are hexagonal. So in other words, they have the Z3 symmetry. And locally, the singularities of this compact orbifold are either modeled on C3 mod Z3, which we know how to resolve, or the further quotient by our involution, which we also now know how to resolve. However, in order to do this last step, we still require the existence of a nowhere zero harmonic one form, whereas we've only written that harmonic one form down in a local model. So if we look at globally what's going on, the singularity at the origin in this case is actually along, so essentially I'm doing 2 steps now. First, I'm resolving the singularities of T6 mod Z3 to give a compact Calabi-Yau threefold, and then I'm doing the involution. And the singularity at the origin, the A1 singularity, now for the compact case, the 3 manifold is actually the connect sum of a 3 torus and S1 times S2 mod Z2. And you should compare that with the local case, where we, instead of the 3 torus, we had R3, and instead of S1 times S2 mod Z2, we had R times S2 mod Z2. So we need to construct a nowhere zero harmonic one form on this space by sort of taking our local model and trying to extend it basically into the T3 directions. General topological considerations, and I have to thank Johannes. We have had some nice collaborative discussions with Johannes and Lorenzo and Mark about some of these issues. So general considerations show that if you try to do that, you'll always fail, because just because of looking at Euler numbers of vector fields and so on, you always produce a 0 along the T3 as you go outwards from the neighborhood of the singularity that we've resolved. Now, if, as we were sort of discussing partly in the discussion session, if the 0 is sort of suitably generic in some sense, it will give rise to a codimension 7 singularity with topology R plus times CP3. And if, on the other hand, we were able to have a controlled model for this in this particular set of examples, one might be able to produce compact G2 holonomy spaces with codimension 7 singularities. And sort of, I think Dominic and Spiro had this in the back of their mind in their paper. This might be a setting in which one could get around some of the problems, technical problems. And there's a natural physical interpretation, actually, of this phenomenon. If you look at the local model, so you can actually see where this comes from. The fixed point set of sigma in C3 mod Z3 is just R3, a special Lagrangian R3, but this R3 is actually singular. You should really think of it as the union of 2 half copies of R3, which meet at a conical singularity at the origin of C3. And when you resolve this, when you resolve the ambient Calabi-Yau, it replaces the origin in R3 by an RP2. So essentially, one is doing a sort of real algebraic geometry blow-up procedure. But if you think about then what's happening asymptotically, you have these 2 sort of ends, 2 copies of R3. And in the case where you have a circle instead of R plus, one can interpret these two ends as D6 branes in type 2A theory, actually sitting on top of what are called O6 planes. But in the compact model, these D6 brane ends have nowhere to go on the T3, and they essentially have to intersect. And this physically will produce chiral fermions, and geometrically should produce a codimension 7 singularity. So it's nice that there's a physical interpretation of the topology in this example. So this is my last slide. So this and other examples like it might be promising arenas for understanding better codimension 7 singularities. And in general, hopefully I've convinced you that trying to understand codimension 6 singularities in G2 seems both physically and mathematically interesting as well. So thanks, and I'm really sorry for running over time.
Well, thank you, Bobby, for this nice presentation. Are there any comments, questions? Well, I have one which is more of a physics question. When you try to tie those codimension 6 singularities to 4-dimensional field theories, you're dealing with massless strings, so that those are field theories with infinite number of states, right? They are non-Lagrangian field theories associated with this BPS string becoming massless?
Yes, I mean, most likely, yes. In general, yeah. Analogous to the 5-dimensional theories. In general, it's very difficult to say too much about. I mean, it's very difficult to say a lot about what sort of theories you have, but hopefully by looking at the sort of discrete data and things like that, one could argue, about the various phases in the infrared. Is it a gap system? Is it a conformal system, or so
on? Hey, Bobby. I have another physical question. So, yeah, here's Tian. So,
oh, hi, Tian.
Is there any relation between? Yeah, hey. So, is there any relation between the 5D tensionless string that you mentioned and the 60 tensionless string that come from basically M2 strings? You have any comment on that? Yeah.
Hang on, which 60? Which 60 one?
Like you have M5 branes, but you have M2 branes stretched between the M5 branes. So there you have tensionless strings. And now in 5D, you claim there's tensionless strings come from M5 branes. Any relation between this two strings here?
There probably are in some dual description, the sort of things that people like Giotto and others consider, 5 branes wrapped on Riemann surfaces with various kinds of boundary conditions at cusps and so on, might give a sort of dual description of some of these systems. But there are probably other physicists who know more about this than me present that want to comment.
Okay, cool, thanks.
Simon, I think I noticed you wanted to possibly say something, or if anyone who wants to talk, please raise your hand also in the chat or in the participants list.
Yeah, I was, for the question you raised at the end about constructing, using the zeros of the harmonic one form to construct, presumably what one needs is an appropriate model for what to glue in around that. But that's what's missing, I suppose.
Yeah.
Is there a,
That's something that, at least in this particular example, because everything's fairly explicit, or actually everything is explicit in the example that we're looking at. Jason and I are hoping that we could make an appropriate model for how to extend the harmonic one form that exists in the local model, how one can extend it into the T3. But but presumably the first step is to make a model on just on R3 essentially. That's what we've been discussing a little bit.
Okay, thank you. Sakura, please go ahead.
Yes, hi. Quick question about the model that you discussed with Jason. Do you know what the four-dimensional theory is? Do you have any other information about what characteristics it has? Should it be a conformal field theory or?
Well, yes, it depends on where you are in the parameter space. So you've got the radius of the M theory circle, and you've got the size of the CP2, and you've also got the size of the Iguchi-Hansens that you're gluing in. So you have all of these parameters, and in some limits, I can say, in different limits, I can say different things about the physics.
So the strong coupling limit, do you know what? Basically, it should be like is there a gauge theory description?
Well,
go to some strongly coupled form.
I mean, you can sort of think of it. If you take the strong coupling limit and you collapse the CP2, then I can say something about the degrees of freedom at the codimension 7 singularity that remains.
Mm-hmm.
But I don't know how complete that description is. I can say something about the degrees of freedom there.
Because the avatar of that theory is just the theory, the P2 theory, right? You could collapse the P2 in that model. You get to canonical singularity. So that's a rank 1 Seiberg theory. And that's actually a theory that's known to be non-Lagrangian. You don't have a way of writing it as an SU2 gauge theory.
Yeah.
So it would be actually interesting to know what the four-dimensional reduction of that theory is. So I think this is what you're essentially constructing. Because we know, for example, the flavor symmetry of that, we know it has a Z3 one-form symmetry. So it would be actually nice to see what the physics of the 4D theory is that you get.
Yeah, so I don't know exactly what happens if you just compactify in a circle, but when you compactify on a line segment, I can say...
So you can go to a generic point in the Coulomb branch and then do the compactification, you just get a bunch of U1s with some matter.
Yeah.
When you go to a strong coupled point, it's not clear what it is.
Yeah, so for small circle and strong coupling point in the sense of the collapsed P2,
mm-hmm.
I can say something about what are the degrees of freedom at the codimension 7 singularities.
Okay, that's cool. Very nice.
I think you're muted, Miriam.
Dominique, your turn.
Thank you. So there's something that I didn't understand. I think you were saying that you're taking a Calabi-Yau 3 metric on the canonical bundle of P2, and then you're taking the anti-holomorphic involution on this, which essentially fixes the canonical bundle of RP2, which is RP3 take away a point. And then you said you had a non-branching harmonic 1 form on this canonical bundle of RP2. Yeah,
no, so it's actually a Z2. It's a Z2 twisted one. So it's on the universal cover. So it's on R times S2 essentially.
Okay.
And it's on R times S2, and the natural sort of variables because of the symmetries of the problem is sort of spherical polar coordinates, and it's just the one form is in the dr direction.
Okay, right. I got something wrong. Good. But presumably if your one form is shrinking towards infinity, then the size of the resolution gets small towards infinity.
Yeah, because you want to go towards the flat model at infinity. Yeah.
And that doesn't cause any problems.
No, I mean that's what you sort of expect. It's the sort, you end up with essentially, in something like a QALE type metric, which is sort of locally flat at infinity.
Well, but you'd think the curvature would actually go to infinity as you go to infinity.
Maybe you mean the derivative of the one form goes to 0, becomes constant as infinity.
I was thinking the size of the one form goes to 0.
Yes, the size does go to 0. Yeah.
So the S2s you're inserting are getting smaller and smaller.
Yeah.
So
that would be somewhat reminiscent of the metric, well, I think metrics you studied and that Yang Li studied on C3, where you have a,
right.
Yeah, same kind of.
So maybe we should conclude this the question period after the talk, and shall we regroup in 5 minutes and continue with the discussion session that is going to be about 45 minutes only.